why do we need pre-trained model for fine tuning, and what are the different aspects when the pre-trained model does not fulfill the requirements while fine tuning it on domain specific data. And also one more question, why do we move toward the LLMs or large language model building from scratch when we already have pre-trained models available? Let's make sure we have a strong foundation in place. A good Python understanding is required, and if you are already familiar with language model training methodologies and working with large language model, then it is a good thing. Also, deep learning and machine learning concept will be more helpful to understand these concepts. Otherwise, I would like to recommend to go to first get understanding the of the basic topics here. Let's see the objectives, what we will be able to achieve after the whole discussion. So we will discuss the important concepts of pre-training and its relationship with fine tuning. Then we will explore why pre-trained model is important for successful fine tuning, and we will go through the practical steps to make it happen. Let's move toward agenda. All right, here's the game plan for today. We will be going through this presentation with this agenda. And now let's begin with this beautiful quote about the pre-training and fine-tuning. Imagine this data is the raw material and pre-training is the foundation we build. What about the fine-tuning? Well, fine-tuning is that stage where we craft the masterpiece and together they work their magic and transform the data into intelligence. Let's see how they work. Let's begin with an introduction to pre-training and fine-tuning to understand the basic concepts. So pre-training and fine-tuning are basically two key phases in training a large language model. During pre-training, we use a diverse and large data set to teach the model language pattern and structure. On the other hand, fine-tuning takes that pre-trained model and then refine it using a smaller but task-specific data set. So this makes the model more specialized and capable of generating contextually relevant responses. It's like giving a general artist some extra training on a specific style. They become a master in that style. So let's see the need and different aspects. Now let's address the most important question here. We have different questions that we are going to address. First, why do we need pre-trained model for fine tuning, and what are the different aspects when the pre-trained model does not fulfill the requirements while fine tuning it on domain specific data? And also one more question, why do we move toward the LLMs or large language model building from scratch when we already? So answering this question, like pre-trained model offer a foundation of general knowledge and language understanding that can be fine-tuned further for specific tasks. So increasing the speed of training and enhancing the performance, it is basically needed. That's why we prefer the fine-tuning of a model. And the answer to the second question is, in some cases, when we have just classification and categorization tasks, then for this we have no need to use the pre-trained LLM. For fine tuning, so we can simplify using classification algorithms to get much better results because these pre-trained models are not suitable for each and every task. So we have predefined algorithm for the classification purpose. So means to say that uh, this is the reason where we choose another aspect for pre-training or fine-tuning a model. LLM streamline the process of creating custom language model by providing the versatile foundation. They also save the time and resources as compared to building the entirely new model from scratch. But when the targeted LLM has not available such parameter as we require, then we move toward the LLM building from scratch. And no doubt it is quite time consuming, costly, and as well as challenging task. So why we have some important reasons that tell the need of fine tuning a pre-trained model. This is the question here, that why we need a pre-trained model for fine tuning. So pre-trained model have already a lot of language knowledge from extensive data set, and fine tuning is something like training those models to specific task or domain. It's like wearing a suit that's perfectly crafted for you rather than off the rack. This example best fit on this topic. So specifically to save cost and time, training time, to promote the transfer learning using different resources efficiently, and allowing for it allows for quick iteration. So it somehow proved as more helpful. Let's see and discuss some pre-training techniques. We have like mask language modeling, autoregressive language modeling, and bidirectional training techniques. So we are using the mighty transformer architecture here. Then there are next sentence prediction, document level pre-training, multitask pre-training, and knowledge incorporation, as well as prompt engineering, which is also specialized architecture that add style to the process. So mask language modeling technique basically utilized here to predict the missing word within a sentence to learn the contextual relationship. Then we have auto-regressive language model, which is helpful in generating text one step at a time, using previous word for context. Then bidirectional training, train a model to understand context from both preceding and as well as the succeeding words. Then transfer architecture is here, which leverage self attention mechanism for efficient and effective learning. Next, sentence prediction. Here, if the sentence if the sentence follow another, adding an understanding of the relationship, then we use next sentence prediction technique there. We have then a document level pre-training, which helps us in pre-training on full document, capturing a long range of dependencies. Then multitask pre-training helps us to perform multiple tasks to improve the overall performance of a model. After this, we have prompt engineering, which is most important thing here, to craft effective input prompt to extract the desired response. Then we have specialized architecture, which is basically designing model to perform specific task on a specified language. So next we have fine tuning techniques. All right, let's see these techniques and how these are working. It's like preparing a recipe, so each step is necessary. First we get our data set ready, then we make sure that the data set is pre-processed just right. We carefully select the model suitable for the task, and then design a task specific architecture. Now how do these techniques help the model fine tuning? So dataset preparations helps us in compiling and organizing relevant data to be used for training an AI model. Then we have data pre-processing, which is helping in cleaning and transforming and formatting the raw data to transform it into suitable format for model training. Then we have model selection, choosing the appropriate algorithm or architecture to build the AI model. Then we have task specific architecture, which is basically useful in designing a model structure tailored to the specific problem which is being solved. Then we have hyperparameter tuning. We basically adjust the parameter of the model to achieve better performance. Then also we choose the loss function definition, which is a technique to help in quantifying the model performance and guide its learning process. Then we have model initialization, which is setting initial value for model parameter to kickstart the learning process. Then training phase begin. It is a phase where the model learns from the data through the iteration to improve its prediction. Then we have validation and monitoring. Here we evaluate the model performance on some kind of unseen data during training to prevent the overfitting. So we have early stopping, which is basically used to terminate the training when we since where the model's performance stop to prevent unnecessary computation. Then we have regularization technique, which applies some techniques to prevent overfitting by adding constraints to the model learning process. at the end we have checkpoints which save the model state at interval during the training to resume from a specific point if needed. Okay, let's see the implementation phase. We have different implementation aspects. We will talk about them in further slides. Before starting the training phase, we need to see all the aspects associated with the model training, like their cost and the model convergence, their memory management and data, as well as model and pipeline parallelism. All those topics regarding the model and resource adjustment will be discussed in coming lecture in a detailed manner. So transfer learning, especially with the transformer, is the go-to in the NLP world. But what about cost? We are going to discuss something about cost. So big models, we all know that like these mean big expenses. As training GPT-3, for instance, could cost around 4.6 million, and it also involves a lot of trial and error. So hyperparameter tuning alone can make the cost skyrocket. So we need a careful consideration here about this matter to maintain the cost of a model, which is needed in training and both fine tuning. So we are going to discuss the conversion phase and implementation. So converting a pre-trained model for transfer learning is not an easy task. Fine tuning those big models needs special care. If we are not careful, we might face different errors. So here are some techniques in our discussion, and let's see how they are working. So we are utilizing reduced batch size, which basically decrease the number of data samples to proceed in each iteration, which can also reduce the memory usage but might impact uh, convergence speed. Then we have gradient accumulation. What is the role of gradient accumulation in this phase? So it basically accumulate the gradient over multiple mini batches before updating the model weight. It also helps in simulating larger batch size. And then we have gradient checkpoints. Gradient checkpointing, which basically store intermediate activations during the especially when the backward pass is processing to trade off memory for computation in memory intensive models. Then we have zero offload, which is basically helpful to reduce the GPU memory consumption during the training. And then we have zero DP and shaded DP, DDP, which is basically zero deep speed approach for memory optimization through both gradient reduction technique, as well as we are utilizing the model parallelism here. Then specifically we have model parallelism. In this phase, we basically divide a model into smaller segments, and each residing on different devices or different GPU, and enabling the training of the large language model. Then we have pipeline parallelism. So in this phase, we split a model into sequential segments where each segment runs on a separate device to reduce the memory usage. Let's see memory. Let's see what take up the most space during the training. That's what we are going to discuss now. So each of these phases require the model to reserve some memory. The forward pass require the model to store the input image, and the intermediate activation of each layer and the output activation of each layer. Then the backward pass requires some kind of information which require the model to store the gradient of loss function for each layer, as well as the intermediate activation of each layer. Then optimizer steps required the model to store the gradient of the loss function for each layer. And then current weight of the network is also updated. So the forward pass is typically the most memory intensive phase, followed by the backward pass and the optimizer steps. In order to reduce the amount of memory required for the training, it is quite possible to use some techniques like batch normalization and weight decay. Then batch normalization helps to stabilize the training process. That's why we are highlighting it here by normalizing the activation of each layer. So weight decay helps to prevent the weight from becoming too large. Let's see the memory management and training. So reducing batch size does not mean everything gets smaller. Here are some different components which are needed for further processing. So we have model, which basically model itself, which consists of the weights and biases of the different layers. Then we have gradient, which is the loss function with respect to the model parameter. Then optimizer state is there. It is basically used to update the model parameter. Then we have intermediate activation, which is the activation of the intermediate layer of the model. And we have to double check the model precisions and see how it affects the memory usage. For example, memory management, we can identify the components that are most memory intensive. For example, if the model is too large, it may be necessary to use a smaller batch size in order to reduce the memory requirements. And why we are reducing the memory requirements to optimize for the gradient as well as for optimizer state. Similarly, if the sequence length is very large, it may be necessary to use a smaller batch size to use the techniques such as dynamic batching. But I would like to tell you something there. In addition to the batch size, the sequence length as well as the memory requirement of the different component can also be affected by the optimizer used. Some optimizers such as Adam and these are basically more memory intensive than others. Then we have model parallelism. All right, if you have got several CPUs and you are splitting the model, sound tempting, right? But surprising, it is not that effective and efficient after all. The model is basically in this phase where we are performing the model parallelism is divided into smaller number of layers, and each layer is associated into is assigned to a different GPU. The array between the layers represent the flow of the data between the layers, and the forward pass of the model start with the first layer, where which take the input data and produce some intermediate outputs. Then this output is further passed to the second layer, which basically produce some more intermediate outputs. This process continue until the final layer, which produce the output prediction. So let's see the backward pass. The backward pass of the model start with the final layer, which actually calculate the gradient of the loss function with respect to its output. And these gradients are then passed back through the network layer by layer. At each layer, the gradient are used to update the weights of the layer. And if you see the model parallelism scheme and image, it allow the forward and backward pass. So it is basically executed in parallel on the different GPU. This can significantly speed up the training of the model. So now we see the pipeline parallelism. To really make things efficient, we are taking the pipeline parallelism in action. Imagine executing several mini batches in forward pass all at once. It's like serving multiple courses in grand feast. So let's see how it works. The model is divided into number of stages, and each stage is assigned to a different worker, and the different stages represent the flow of data between the stages. So the forward pass of the model here start with the first stage, which take the input data and proceed some intermediate output. Then output are passed to the second stage, which proceed some more intermediate output. This process continue until the final stage. Then to produce some kind of output prediction. Then the backward pass of the model start with the final stage, and it calculate the gradient of the loss function with respect to the to its output. So the gradient are then passed back to the network stage by stage. So at each stage, the gradients are used to update the weights of each stage. Here we are done with the pipeline parallelism. Then let's see the challenges. So there are challenges these are the challenges we face during the both phases, like pre-training and fine tuning. Is as we know that data quality matters a lot. Then resource intensity as well as domain specificity. Then some fine tuning challenges are also here, like domain adaptation and overfitting, some kind of bias mitigation problems, and optimization as well as generalization. So they are all part of the journey from the pre-training challenges to the fine tuning challenges. So each hurdle refines our approach. So conclude the whole discussion about pre-training and fine-tuning. So it's a dynamic duo that equips model with broad language understanding and domain-specific knowledge. Models might still produce biased or inappropriate content. So it's our job to carefully design the data sets